Many prophets of doom and gloom constantly predict the most horrendous woes that will befall us. As an example, think about Y2K. In that case, many computers were supposed to not work after the 1st of January of the year 2000. Didn't happen. Computers kept on working. The same is true for so many of these other predictions of bad things that are about to happen. One warning that we've seen over decades now is that of the imminent demise of IP version 4. The problem is that we are running out of IP version 4 addresses, and that would curtail the growth of the Internet. Internet has kept on growing. However, in this case, the warning has merit. We are at a point where we can no longer postpone solving the problem. The solution has been around for a long time, IP version 6. So in principle, it should be easy to fix the problem. However, there are quite a couple of reasons why it is hard to fix it. There are also quite a couple of reasons why we were able to postpone the problem for such a long time. The reasons of why we were able to postpone it for such a long time will be the theme of the next video. In this video, we will look at IP version 6. We will mainly look at IP version 6 addressing, but we will also touch on IP version 6 routing. A quick remark about the videos that deal with layer 3. Originally, I planned to produce 5 videos to cover layer 3, and I plan to cover the topics in today's video in about 30 to 40 minutes of video material. However, today's video stretched over more than an hour, and I deemed that to be too long. So I sliced it into 2, and the video series on layer 3 now consists of 6 videos, even though earlier videos indicated that the series would only consist of 5. Let's start our discussion of IP version 6 by looking at IP version 6 addresses. Just to provide some context, recall that an IP version 4 address consisted of 32 bits. So if we were to draw it to scale, then let's say that represents a 32-bit value. An IP version 6 address consists of 128 bits, so it is 4 times as long as an IP version 4 address, so it will look like this. Perhaps a better way to get a feeling for the size of an IP version 4 address is to write out an example of such an address. Again, for the sake of comparison, remember that an IP4 address may have looked like something like this, 10.1.2.3, something you can easily remember, something an IT tech can tell a user to enter into a box. An IP version 6 address is obviously going to be a much harder value to remember or to write down. But just to appreciate how hard it may be, let's look at this example. An IP version 6 address will be written down as 8 fields, where in every field you represent 16 bits. Let's denote the 8 fields quickly. As you can see from the way in which we've denoted the fields, IP version 6 will use colons to separate the fields, where IP version 4 used dots to separate the fields. Every field in an IPv6 address will consist of 16 bits that are written down in hexadecimal. So we may have something like the following. Clearly, that is a much harder field to recite, to remember, for an IT tech to give to a user to enter via a phone line. There is one thing that makes our life a little bit easier. We can write, or we don't have to write down leading zeros. So in our example that we have here, there is a leading zero. We don't have to write that down. There's another leading zero. We don't have to write that down. Well, there are quite a bunch of leading zeros there as well, and that's it. So a somewhat shorter version of this address would therefore look as follows. Clearly, that is still a very long address. But one of the tricks that IPv6 has up its sleeve is what is known as zero suppression. So what I've just done by cancelling the leading zeros is not zero suppression. What zero suppression is where you have a couple of fields. As we see in this example, there are a couple of fields that consist of sequences of zeros. And we can write them down with a very brief notation that just says, fill this value with zeros, or fill this entire missing portion with zeros. So let's illustrate that with an example, because that's the simplest way to do this. So what I've done here, I've copied the initial bunch of values, and now we get to the sequence of zeros. And rather than writing them all down, we're going to write down a second set of colons with nothing between the two colons. And then we're simply going to write down that final field, which happens to be A350. Now, anyone who gets this address will realize that we don't have all 8 fields that we should have. They will immediately see the 2 colons following one another, and they will stretch that out and fill that or pad that with zeros. So the zeros have been suppressed, and they can easily be unsuppressed again. Clearly, we can only do that in one field for a specific address, because if we were to have an address that looked, let's say, like this, A colon, 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 B colon, 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 C, then we would have had to stretch everything between A and B, but also stretch everything between B and C, but we don't know by how much. So the 2 fields there and there cannot work. But with a single field like that, it's easy. We just stretch it out until it fills 128 bits. Still hard to write down, but at least it is somewhat simpler. The way in which we will eventually assign addresses will make judicious use of that option. We will specifically assign addresses or allocate addresses to machines that need to be written down fairly regularly, let's say routers, to have lots and lots of zeros in them, so that they contract to something that is as small as possible. In the first video on IPv4 addresses, we were faced with a challenge. How do we split the address between the network number and the host portion? We, in principle, have the same problem with IPv6, but rather than inventing classes A, B, and C, and so on, they decided to use a much, much simpler solution. So if our IPv6 address looks like that, 128 bits, then the split will be made there. So 64 bits will be allocated for the network portion, and in this particular case they introduced a very nice new notation that they call the routing prefix. So the routing prefix, initial 64 bits, and then we still have the host portion at the bottom. If we have a routing prefix, if we have a network address, then we can address 2 to the power 64 hosts on that network. It's what we can always do as a quick calculation. You know that 2 to the power 10 is more or less equal to 10 to the power 3. So what that means is 64, we have 10 plus 10 plus 10 plus 10, there are 6 of those. 2 to the power 60 is more or less equal to 3 times 6, 18. And since this is 64, 2 to the power 64 would be equal to more or less 16 times 10 to the power 18. Stated a little bit differently, we will have 16 we will have that number of hosts that we can address on our network. So in South African and British proper English, that would have been 1 million, that would have been 1 billion, that would have been 1 trillion, 16 trillion possible hosts on our network. Now we all know that the Americans went to 1 million, and there they decided that they're going to call that 1 billion, they're going to call that 1 trillion, that's probably a quadrillion, and that's probably a quintillion. So in American English, which for these numbers is probably used all over the world nowadays, it means 16 quintillion possible hosts on our network. By the same token, we have more or less 16 quintillion, or in South African British English, 16 trillion possible routing prefixes. That is a lot of prefixes that can be handed out to companies, and whenever a company gets such a prefix, it can address a lot of machines. This address space is huge. Where does one get a routing prefix? The answer is exactly the same as it was about IPv4. Where do you get a network address? You will ultimately get it from your regional internet registry, but they will probably have divided it already and handed it over to ISPs to hand over and so on. One of the decisions in IPv6 is that a local internet registry, someone on a local level, who is able to hand out addresses, will at least get a 32 block. The notion of private addresses has been carried over. Recall that in IPv4 we had the 172.16 2.31 and the 192.168, followed by whatever as Class A, Class B, and Class C private addresses. To pick an IPv6 private address, you simply use the network prefix FC/7. Written out, it looks like this. So that notation says the first 16-bit value is FC00. The colon means pad with zeros until you get to 128 bits. So the remaining 7 fields here will all be zeros, and then only the first 7 bits are important. In binary, this would mean translating the F, that's 1, 2, 3, 4. C, remember A is 10, B is 11, C is 12. So it is 8 plus 4, and then 0, 0. So that's simply the FC written in binary. If you want to write down the remainder of that field, you can do that. But one of the things that we see from the /7 is that only the initial 7 bits are important. So that's what is important. That is not important at all. In fact, those zeros were not important apart from the fact that we needed them to position the FC right at the left-hand side of that field. So if you start an address with this value, it is deemed to be a private address. The special case is 111110. That indicates we're dealing with a private address. But then as a sort of a sub-address of this, if you want to, they say let's make that a 1. The prefix that they end up with out of this is, that is an F, that we've just increased by 1, so that is a D, and we still need to position it to the left-hand side of the leftmost field. So we're going to again say fill up everything that follows with zeros, and now we are interested in the first 8 bits of this field. The way that the private addresses in this range works is as follows. You're going to use the 8 bits that are prescribed. You're going to insert 40 bits of a random number. The random number is intended if I were to pick a private address and my neighbor pick a private address, then chances are that we'll pick different random numbers. And our addresses, even though we selected it from the same mechanism, will most probably be different. In fact, if you think about it, what are the odds of picking the same number from a 40-bit field? So a 40-bit field, again, means 1 billion in one English and 1 trillion in another English. So the odds of selecting the same value by 2 parties is about 1 in a billion or 1 in a trillion. It will hardly ever happen. In fact, what this means is if you pick an address, then a private address, and you just pick a random number to put in there, you will probably have a unique address on the internet. And you may be able to use this as a unique address, even though it was not assigned to you in any way. It will not be the same as anyone else's. As I said a moment ago, our particular concern is where 2 networks with private addresses are connected. They will definitely be different. And we will often get that where a company connects to, let's say, an ISP, and the company has a private address, and the ISP also has a private address. Now, following this, they allow you a 16-bit subnet field. So in your company, you can now have 2 to the power 16 different subnets. And now we eventually get to the host portion, and you can have or can use all 64 bits to indicate which host on one of your 2 to the power 16 possible subnets you're talking about. Sometimes it's slightly easier to think about these addresses by drawing little pictures. So the private address that we've just looked at will consist of fields that look as follows. You will have 8 bits, and they will contain the value FD to say that you're using one of these special private addresses that have been categorized for private use. Then you will have random bits, 40 of them, just to make your selection different from anyone else's. Then you will have a subnet, and that will be 16 bits. And this takes you to your routing prefix, that is 64 bits long, and my picture obviously not drawn to scale, but there you will have your host portion, which is the remaining 64 bits. In terms of routing, IPv6 makes provision for 3 types of routing. Ironically, the terms all come from the word broadcasting. They all use the casting suffix, but IPv6 does not support broadcasting. Obviously, that raises a couple of questions, and we'll touch on them just now. But the 3 types of casting it allows is unicasting. Unicasting is when you send information to a specific machine, just to that one IP address. So there's no real casting involved. You just route it to that particular host. Then multicasting is supported. And multicasting is more or less what we've encountered in IPv4, but this is a much upgraded version of multicasting. Multicasting is when a message is sent to a number of machines that have some common interest, that are in some group. Our example from IPv4 also applies here, where you use multicasting to send a message to all routers. So it is broadcasting to all routers or to all other machines that have something in common and therefore need to be addressed, need to get the same message. But as I've said just now, no broadcasting is supported whatsoever in a general sense. And then the final casting is anycasting. Anycasting is used when you have machines that do the same job, but for the sake of redundancy, you have more than one machine. The other machines, let's say you have 4 machines that do the same job, 3 of them are not failover machines. In other words, the idea is not that one machine does the job, and when it can't, then the second machine takes over, and if it can't, then the third one takes over, the fourth one takes over, and so on. The idea is rather that you send an address to a pool of machines, and then any one of them can get the message. Very useful for load balancing. If you think about web servers of very busy companies, they may use anycasting, and then your query, your web search query, may be answered by any one of them. Yes, the user will not know which one answered you. Anyone could answer you, and from there the word anycasting. Without support for broadcasting, there are a couple of things in IPv6 that may seem hard to do. One of the examples where we used broadcasting in IPv4 was for the Dhcp Protocol. A computer joined the network, it didn't have a static IP address, and it sent out a broadcast to the network to say, listen, hosts, do any of you know what my IP address is, or can any of you give me an IP address? In IPv6, that message will not be sent to the entire network. It will use multicasting, and it will send it to the routers. So multicasting solves that problem. If you used DHCP in IPv4, you encountered a different problem as well. You had to specify a source address. Where did this message originate from? And we used the special address 0.0.0 to indicate the origin of such a message. I sent that message. I don't have a number yet, so I'm calling myself 0.0.0.0. There are other conditions where a network or a node on a network may also need an address, and where it may be hard to obtain one. There are, in essence, three ways of obtaining an address. The one mechanism you can use is to assign an address statically. Means a network administrator assigns the network beforehand. The other option is where you obtain the address from a server or service like the Dhcp. And then the third option is the one that IPv6 now uses, that of auto-configuration. Auto-configuration means that the address is sort of generated by the machine that needs it, but it's generated in a way that will not be the same as an address that was generated on another machine. So to indicate an auto-configured address, IPv6 has allocated or selected the prefix FE80/10. Again, the colon means that you pad that whole field out with zeros. Only the first 10 bits are fixed, so it means the remaining 118 bits are available for this auto-configuration process. Perhaps it's worth just looking at this address to fully understand what we are dealing with here. The FE80 was again written out using 4 hex digits to make sure that the F ends up in the leftmost bit position of this 128-bit field. But if we look at the 10, it means those 4 bits representing the F, in other words, 1111, let's write it down, 1111, are of importance. The next 4 bits are also of importance, and then we've already used 8 bits and only 10 of them are important. So the moment that we write the 8, it would be 1, 0, and in principle 0, 0 again, but this already takes us to 10 bits. So if we, for example, auto-configure this to become 1, 1, then it means that auto-configuration prefix will still be an F, it will still be an E, but this third byte that we've now configured with a 1, 1 will become 8 plus 3, that is B. So it looks, by inspection, looks very different from an auto-configured address. So you should be careful. You can get values that do not look like auto-configured addresses, but they are indeed auto-configured addresses. Now, to determine an auto-configured address, a computer will attempt to use values that are unique to it. And one of the values that is unique on almost every network interface card nowadays is the MAC address. We will only talk about MAC addresses when we talk about layer 2, so in the next couple of videos. So we're not going to say too much about it, but one of the things that you will see when we talk about MAC addresses is that they are assigned to be unique globally. You're not supposed to get 2 MAC addresses ever that are the same. So if you use that, which happens to be a 48-bit MAC address, and you push that into a field where you have 128 minus 10, 118 bits available, you can see that it's pretty easy to come up with an address that is indeed unique. So every machine that boots up and has IP6 configured will auto-configure an address for itself, And then when it, for example, sends out a message to the DHCP server, which at this stage it doesn't know which one it is, so it's a multicast to all routers, it will use its auto-configured address that will look like that, with the caveat that it may look slightly differently in some cases. Also, when two machines want to talk to one another, they already have these auto-configured addresses and they can start talking immediately without the need to assign any special addresses to them or any third party to become involved in this process. There is another way to interoperate an IP version 4 network with an IP version 6 network. You will recall that IP version 4 uses a 32-bit address. IP version 6 uses a 128-bit address. So can't I just take this 32-bit address and put it into a 128-bit field and use it? And the answer is sort of yes. Not everything I can do in IP version 4 will still work, but normal communication will work. And the mechanism that was proposed for that is to use addresses of the form colon, colon. In other words, let's use all zeros, and then at some point I'm going to say if all ones. And following this, I will encode my IP version 4 address, the 32 bits. So in this field here, clearly we are using 16 bits, and I am now going to add my 32 bits to indicate my IP version 4 address. Now, I guess one option would be to take my IP version 4 address, take the 4 bytes, and write those two in hexadecimal, and write those two in hexadecimal. But the designers thought it good to make our life a little bit simpler, and they said, let's take this notation that we are used to in IP version 6, the colon hexadecimal notation with zero suppression, and let's use the dotted decimal notation as a suffix to that. So I can say something like 10.1.2.3. Now this address, and you can see that I'm not filling up the host portion fully, so to get the full host portion, I would have to pad this with a couple of zeros. So the zero padding in front pads not only the routing prefix, but it also pads a little bit of the host portion. But the point is that whenever I use an address like that, so this indicates it's IP version 6, but there it means I'm going into IP version 4 compatibility mode. I'm actually using an IP version 4 address as an IP version 6 address. In order to make this more concrete, let's play with this in real environments. So what I'm going to do, first of all, here I have a Windows command line interface, and I'm going to say ping, and I want to ping an IP version 4 address, 10.1.1.1, but I want to use the IP version 6 notation for it. So if colon 10.1.1.1. Clearly that is a lot of zeros, followed by this if marker, followed by a dotted decimal notation address, and I am getting my responses back as I would have expected. Little experiment, if I say ping and colon FFFF, but now I want to translate or to encode the 10.1.1.1 in hexadecimal. I'll leave the conversion up to you, but it is A01 for the first 16 bits and 101 for the next 16 bits. I've used colons here, no dotted notation, and what you can see is I'm getting exactly the same responses back. So it doesn't really matter how I'm encoding it, whether I'm using the dotted format or whether I'm using the colon hexadecimal format full out. One other thing on this computer before we move to the next one, if we do an IP config because this is a Unix machine, Windows machine, then there you see that we have an auto-configured IPv6 address. It starts with the prefix FE80 as we would have expected, and then some lower level values that if you're interested you can go and work out how they've been derived from the MAC address. Let's now move to Linux computer. Actually, this is a Raspberry Pi, Raspbian. And first thing that I'm going to try is to do exactly the same ping that I've done, except in this case, this machine is unfortunately not entirely correctly configured for it. One interesting thing to note here, if I type in ping and I use tab complete, you'll see that I have 3 versions of the ping command. A ping which will automatically select what should happen, a ping 4 which will force you to use IP version 4, and a ping 6 which will force you to use IP version 6. So I'm going to pick ping 6, and I'm going to say exactly the same colon FFFF and then 10.1.1.1. It does not want to access my IP version 6 network from here. However, interestingly enough, if I force you to use ping version 4, and I use this IP version 6 address or IP version 4 address in IP version 6 notation, in other words, the FFFF followed by the 10.1.1.1.1, then I do get a response. Similarly, if I force you to use IP version 4, and again specifying the IP version 6 address, and this time around I'm going to not even try and use any IP version 4 notation, then I also get the response back. Look at the, let's tap that down a little bit, if config on this machine, then you will see that there is an INET6 address there. And it has in fact been auto-configured. You see the FE80 prefix. So this is not something that I've assigned. It just exists on this machine. If I say ping 6, then you can see I am effectively pinging localhost here, and ping 6 works perfectly. If I go to my Windows machine and I say ping, just to show you that ping 6 is not installed here as such, but if I say ping and I provide the Raspberry Pi IP version 6 auto configuration address, I am getting my replies from it. Typical Windows behavior. I am getting these 4 pings with responses. Going back to the IP config, and I copy the IPv6 address from here, which, as you can see, is again an auto-configured address, and might as well clear the screen, and I say ping. In other words, I'm now pinging this local machine with its own IPv6 address. It pings it very short response times because it is the local host. But going back to the Raspberry Pi, if I ping 6, the address that I've just copied from the Windows machine, then it happily pings it with ICMP sequences and everything else indicated. So clearly routing is working here. I'm getting IPv6 out, I'm getting IPv6 in. I've not yet set up proper addresses on these machines using the appropriate private address space that I will probably use, but that is immaterial for the time being. It would be a simple matter to do that. In earlier examples, I pinged the machine on which I was working by using the auto-configured address of that machine. However, this raises the question, is there a local host address, one that always refers to this machine, without me having to look up some auto-configured address? And the answer is yes. In IPv6, localhost is denoted by a string of all zeros. With zero suppression, that means the address becomes suppressed to just colon, colon. So pinging it would simply mean ping and colon, colon, and I am getting responses back. Interesting question, why am I getting responses back from that particular address? I'll leave that over to you, up to you to go and look at. Keep in mind that this localhost is not only useful for echoing, in other words, for ping commands, it is useful for anywhere where I want to write software, where the software wants to use networking to talk to other software on the same machine. Our discussion of IPv6 provided us with an overview of IPv6 addresses. We were able to talk about the notation used for IPv6 addresses. We introduced the notion of various prefixes, in particular routing prefixes, and we also mentioned the types of routing that are available, anycast, multicast, or unicast. We didn't have an opportunity to look at how one would indicate that an address is a multicast address or an anycast address. We also didn't get around to looking at IP headers, whereas IPv4 headers may differ in size because they contain option fields that are not of a fixed size. IPv6 headers have a constant size, and then if they use options, they use what is known as optional extension headers. This fixed structure of a header makes it simpler and more efficient to route. IP6 also includes a notion of route aggregation. If two destinations are close to one another, then they would probably follow the same route for the earlier part of their journey. And rather than having a single entry for every one of them in the routing tables, one can have a combined entry, a single entry that will route packets to both destinations, or in the end to multiple destinations, as long as they share a route and their route can be aggregated. That means routing tables become much smaller. In our next video, we will look at a number of mechanisms and techniques that have been used to extend the life of IPv4.